Hello, good morning, everybody. This going to be our second class for this Math 244. We started last week. I sent you a video and we discussed it. So we want to, we talked about mean value theorem, and we want to talk about we divided it into two. Especially, we talked about the Rolle theorem, which we said we would use to prove the mean value theorem. So we're going to Rolle theorem. We talked about that, and we talked about there's another theorem that we mentioned. That's the local extremum theorem. The local extremum theorem, which states that okay, let me write it out. This local extremum theorem states that if f is differentiable on an interval AB, then oh, sorry, that's not the local extremum theorem. I'm clearing. Let me clear the. Let me clear the screen. It says that um at a local. Okay, this is local extrema theorem. The local extrema theorem says that at a local extrema, at a local extrema, f prime local extrema says c, f prime c is equal to 0. So we're going to need that today. And so let me restate so that we don't waste our time. I don't have to start asking you to go back to the last video. So let me restate the Rolle theorem. So the Rolle theorem states that let A be less than B if f if f is continuous and differentiable. Okay, on closed interval AB and differentiable on open interval AB and FA equals FB. Then there exists a point C in AB such that f prime, when you take the derivative, f prime C is equal to 0. So that's the mean value theorem. This is a very beautiful theorem. So let me again, because we are proving it today, and it shouldn't take us long to prove it. But interestingly, it takes far longer time to prove it in classes because students would always often call you back. All right, but this time around, there's no student to call me back, so I'm going to rush through it. And instead of students calling me back this time around, they can just go back to the video and see any part of it that it was. So we are saying A and B have the same value on the y-axis. This is the y-axis, and this is the x-axis. So let's say this point here is point A and B, meaning that here we have a FA and is equal to FB. So both of them are here. So let's assume, so this is the interval from here to here. So let me pick another color just to make things exciting a little. So we'll now take let's say this is my curve. Okay, so that's my curve. Okay, let me redraw the curve. Let me redraw the curve. So let me say this is my curve, just for simplicity. This is my curve. Okay, so from here to here, that's f of a. From here to here, that's my f of b. Of course, f of a is equal to f of b. They are both at the same height. All right. So it's just like when I asked you, let's assume that we pack all the students in our class together. We would at least have two of them who have the same height. So let's set those ones at the extreme ends and put the rest in between them. Okay. So that is just the way it is. Another way of sketching this, just to okay. So according to the Rose theorem, it's saying that if that is the case, then there must be a point of inflection, the point where when this thing goes up, when it goes up, the point where it stops going up, okay, and starts coming down. That's what the theorem is saying. And that at this point, if you take change in x, you can have it. But if you take change in y, it's there's nothing to change along the y axis here because it's flat. So that will have to be zero, meaning that change in y over change in x in this case will be zero, which implies that f prime at that point, at any point on that line, is equal to zero. So that's what the whole Rose theorem is talking about. All right, but then as simple as it might seem, the proof is not that straightforward. So now I've cleared my screen and I want to start the proof of the mean value theorem. I want to start the proof of the mean value theorem. The proof is divided into three. That's how incredible it is. It's divided into three. So proof of the mean value theorem is divided into three. So what are we looking for? We are looking for a point C inside A, B. All right, such that the derivative will be zero. That's what we are looking for. Okay. Now, don't forget what we said about mean value theorem. Okay, let me list out the properties of mean value theorem. The hypothesis in mean value theorem. I'll be listing it on every page so that we can always come back to it. F A must be less than B. That's one. Okay. Sorry, I thought. Okay. Okay. Properties. Properties or hypothesis. Hypothesis of Rolle's theorem. Sorry, we are proving Rolle's theorem. Okay, the hypothesis of the Rolle theorem. So the first hypothesis is that A is less than B. That is, we have a line A and we have a line B here, and this is the y-axis. So there is an A that is less than a B. So we have that. Another hypothesis there. That's the first hypothesis. The second hypothesis is that F continues on A, B. Another hypothesis is that F is differentiable on A, B. And another one is that the height of F at A is also the height of F at B. Okay, so now that we have all these things stated out, let's now talk about it. We are looking for a point C between. Okay, so we are now looking for a point C. So we are looking for a point C here. A point C. We are looking for a point C between A and B, such that FC will be 0. Okay, so since f is continuous, of course, we are now taking this one. Since f is continuous on AB, since f is continuous on AB, okay, by the extreme value theorem, by the extreme value theorem, which I think I mentioned, by the extreme value theorem, there exists f big M and f little m on AB. Okay, that is, we have the since f is continuous on AB, then f must have the highest power, I mean the highest value or the lowest value within this interval AB. Okay, it must have that one. That is, so we have, if this is a function, okay, between A and B, there must be the highest point on it and there must be a lowest point on it. That's what we are saying. Okay, now because we have the highest point and the lowest point on this and we are calling the highest point FM and we are calling lowest point FM, it means point M on the x-axis has the highest value and point little m on the x-axis has the lowest value. Okay, now two things are likely going to happen if that is the case at hand. The first thing is that, what if fm is equal to fm? Okay, what if that's the case? What does that tell us? If the largest height in the class is also the same as the shortest height in the class, what can we say about that? It only tells us that this class has what? Think about it. If it were a proper class, I would have awarded 5 marks for, actually like 10 marks for that, because it takes intelligence to know. So if the tallest person in the class is also, I mean, has the same height as the shortest person in the class, it definitely means that everybody in the class have the same height. That is, so therefore, if so, we are talking about Fm being the same thing as F little m. That is the tallest, and the shortest are the same. All right. So this is a scenario. The other scenario is if the tallest person is not the same thing as the shortest person. So now let's consider the first scenario. This scenario is what I've told you, that it means that it means that for all elements within that interval, everybody would have the same height. Fx equals Fm. That is equals F big M. That is, everybody would have the same value. So if that is the case, let me sketch it so that you see it. So we have A and we have B. We already know that A and B have the same value. All right, and then we are saying that if F big M and F small m is the same on the graph, it means that everybody will have the same height, which means that even FA will be the same thing as FB, will be the same thing as FM, will be the same thing as F little m, and will be the same thing as FX for all. So it means that FM will be here, F little, that's hem, hem. So it means that for everything we are going to have, so the function will be like this. What function behaves like this? That's a constant function. F of x equals c. All right, it means that f of x equals a constant function. And from what we've learned of constant functions, what is when you take the derivative of a constant function, what does it give you? It gives you 0. All right, so we know. Okay, but then before I roll into that, yeah, so we know it's going to be 0. So what is our c therefore? So of course, if you take the derivative of a constant function, it gives you 0. Now it means that we can therefore uh, talk about a c, which is going to be we as long as whatever we want, we can say a plus b over 2. All right. Of course, we know that if it's a plus b over 2, it's going to be something in between this, I mean, a and b. We're adding the two together, and we're taking their average. So it definitely means that a c will be in a and b. Okay. If this is the case, if this absolutely is the case, then we're good. We're good to go. It means that we can just select that as our C, which we know that F at that C, and we take the well, it's going to be the same thing as F at A. All right, it's going to be the same thing as F at B. So, and because we are now talking about a constant function, then we can now say F at C will be equal to 0. Okay, so that's explains that. I would explain it better in the class if you have any issues with that. So that's my first case. The second case is a little bit more dramatic. So we call this case 2. All right. Case 2 is when Fm, that is the highest point, is not the same thing as the lowest point. Okay, that's my case 2. That's my case 2. So, let me the hypothesis again. A is less than B. Second hypothesis, F is continuous on AB. The third hypothesis, F is differentiable on AB. And the third hypothesis is that FA equals FB. Okay, so those are the hypotheses. We can always, I'm writing out these things so that we can always go back to them when we need them. Okay, this one is there. Okay, and this one is here. Fantastic. Sure. So let me sketch it. So it's not impossible for it to be like this. We have A and B. We say don't they don't match. Okay, so we say FA is here, FB is here because they have to be on the same line. Then we are saying F of M is not equal to F of M, which means that both of them cannot possibly be on the same pedestal. So it's either one is here and the other one is well, let's say this is hem. If hem is higher, then we are going to have hem here. So it means that the curve would have to go like this, and it will have to come like that. Okay, so well, it's not impossible for little hem f at little m to be smaller than f at a, meaning that the curve. So we can actually have a curve. Okay, we can have that as a curve where this one will be big hem. All right, and so this height here is going to be f big hem. Okay. Okay, we can have that. So you can't be asking me, well, where is my little m? Well, if this curve is like this, it means that little m would probably take the same value as A and B. But then to avoid such nonsense, why don't we even have my A, B here, and A is here, FA is here, FB is here. We have big M here. That is, it's something that can go up here because it's taller than everybody. And we have little hem here, which is shorter than everybody. But then we still know that everything will come up. So we have little hem here, which is shorter than everybody. Okay? Now, this dude here is taller than everyone. This dude here is taller than everyone. This dude here is shorter than everyone. So this is a FM, and this is a F little m. This is a FA. This is a okay. This is FB. Okay, so that's a scenario that you have painted there. So now let's assume that that's the scenario we want to deal we are dealing with. So we know that whatever happens, if FM is not the same thing as F little m, that is the tallest and the shortest are not the same, then we know that at least one of them is not A. That is him, the boy who has the highest height would not be A. It's not going to be A. And that guy will also not be B. Okay? Will also not be B. All right? That's an assumption that we are taking, that FM is the highest point. All right? Okay? So if that is the case, then it means that FM, that is the tallest boy, will be taller than FA, and it will be also taller than FB. I hope you agree with that. Okay, so now let's move on to the next. Let's move on to the next. My phone just fell off. Excuse me, excuse me. Okay. Uh, Shoot. Okay, so I'm just checking my writing pad. Okay, I'm syncing it with my phone, so okay. Sorry about that. All right. So so since m uh is not equal to A and m is not equal to B, and we know that A and B are the endpoints, it means that m would be inside A and B. I hope you understand that. Okay. So we know that m will be within this interval. Since it's not A and B, we know that if it's not A and B, then it can't be the endpoints. If it's not the endpoints, then it has to be within the endpoints. Okay, so it means that it is an interval. It is in the open interval of A and B. So that one has been established. We have established that. Okay, now having established that, we from the hypothesis we know that F from hypothesis of the Rolle's theorem, we know that F is a differentiable on A B. Okay, so if M is differentiable on AB and M is in AB, it means that therefore F is differentiable at M. Okay, F is differentiable at big M. That's what that is telling you. Okay. Okay. So by the theorem, by the theorem of a local extrema that I talked about first. Okay. It means that if that's the case, it means that Fm is a local extrema, which we have established is a local extrema because it's the top, is the highest point between A and B. All right, so it's a local extrema, and from the yeah, it's a local maximum now. It's a local maximum, So and because it's a local maximum, by the local extrema theorem, by the local maximum theorem that we talked about earlier, it means that F at M is the Fm prime, sorry, F prime big M will be equal to 0. That's what it means. So it's going to be equal to 0. So if it is 0, it means that we can therefore set M to be C. All right. And therefore, we have found the C we seek. Okay, so that's a case 2. Now case 2 has a B side. Okay, so case 2B. Okay, case 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 2A is when I consider hem as big hem now as the tallest side. I mean the tallest part. All right. Now, and I'm assuming that tallest part is not having the same height as the extreme points. Okay. So if let's even assume that is now having the same height as the extreme points. Okay. So if it's having the same, if the M part, so this is A, this is B. Okay. So if and the A is here and B is here. All right. So if M is also here, okay, but then we know that this big hem is here. Then we know that small hem can be here and it will be lower than all of them. Since we say, so even whatever happens, we are still going to have a dip because we said that f of hem in this case is not the same as f of as little m. So let's consider this case. If this is the case, that's the case we call case 2B, when we have a local minimum. We want to establish M as a local minimum and show. So normally, I often tell students to go and do this themselves by following the tactics or the technique we used in the first one. But then let me just do it so that we can all appreciate the thing. So case 2B. Now, let's look at the other scenario. Okay, the other side, when f little m is not the same thing as f of A, and it's not the same thing as f of it's not the same thing as f of A, which is the same thing as f of B. Okay, if this is the case, it means that m can't be the same as A, and m can't be the same as a B. If that is the case, then it means that M will be in the interval AB. I hope we have to all agree with that. Okay. Now, so since okay, so it means that, but then since M is the shortest, it means since FM is the shortest, it means that FM will be less than f of x for all other x that is in that interval AB. Okay, so it is the shortest. So that this makes him a local Therefore, Fm is a local minimum. Is a local minimum. Okay. All right. It's a local minimum. Being a local minimum. Um, okay. Well, first is a local minimum that we have established, and we know that F is differentiable on AB. Therefore, F is differentiable at little m as well. Okay. So okay. By the theorem, which is uh, the local extrema theorem. So by the local extrema theorem, okay, which says that every local extrema, the derivative is going to be um, 0. And we have established that little m is a local is a local extrema. So sorry, f little m is a local extrema. So we know that f prime little m will have to be 0. So we can set m to be the c. Therefore, f prime c equal to 0 for c that is between a and b. So we have now found the c we seek. All right. So that's hence the proof of the mean value theorem. In the nutshell, the proof we divide the proof into three. Okay. Let me just call this the recap. The recap of the proof. Recap. Okay, we divide it into three. When FA is equal to FB equals FM equals F little m, which that is for all x that is in the interval AB, for all x that is in the interval AB, Fx is a constant. Sorry, Fx is the same value. All right. So which means that which implies that f is a constant function. So if f is a constant function, it means that f prime c will be 0, or f prime x is for all x element of a b. So that one is settled. Then the second so that's we call this one case 1. So case 2 is when we know that fm, the tallest part, is not equal to the shortest part. So if this is the case, then we look at if we now consider a situation where m is not the same thing as where fm is not the same thing as f of a, which is the same thing as f of b. If this is the case, it means that m will not be the same thing as a, m will not be the same thing as b, which makes that big M an element of AB. Okay, if it's an element of AB, this implies that f is differentiable at m, which is one of the conditions of the Rolle's theorem. So if it is differentiable at m, which we have established, then we know that since m is the highest point, then it means that we can't be talking of any other value. It means that for all x that is in a b, Fm is greater than or equal to Fx. So it makes which makes M a local minimum. I mean a local maximum. All right, a local maximum. All right. So and since it's differentiable, then F prime M, according to the local maximum theorem. I know, please close that door, please. Sorry. According to the local maximum theorem, Fm would have to be 0. Uh, that's that is that. Okay, that's case 2. Well, we call that case 2A. Then we have case 2B, which is the reverse of this. If F little m, okay, sorry, this one is not equal to. All right. So if F little m is less than F big M, and F little m is not equal to FA, and it's not equal to F, which is the same thing as FB. So if F little m, if the height of Fm is not the same as height of A, then there's no way you can mistake M and A. It means that M is not equal to A, and M will not be equal to B, definitely. So since A and B are the extreme points, it means that A, B is such that M is between them. That is how do I put that now? Is within this open interval. If it's within open interval, I'm just doing a recap of the whole proof. If it's within the open interval, it means one thing, but and is the shortest part. It means that for all x that is within that open interval, f at x would definitely be f at m would definitely be small than f at a, which is f at x. Okay, since it's the shortest, then it has to be shorter than everybody, and if that is the case, it means that it makes f m a local minimum. And a theorem that we've talked about earlier said that okay, is a local minimum. Okay, f of m is a local, and f is differentiable at m. Why is this differentiable at m? Well, the hypothesis of the conditions of the Rolle's theorem says that f is differentiable on the open interval a b, and since m is within this open interval, as in like m is within that open interval, then we have no problem confirming the differentiability of f at that point. Now it means that we have gathered everything, so it means that we can just use the local extremum theorem, which says that f at a local extremum, which fm is, the derivative is going to be 0. So we set m to be c. Therefore, f c prime will be equal to 0, which effectively ends our proof. Please go through this video and try to understand it. My assignment, okay, turn the video into a proper note. I'm going to check these notes that I'm seeking when we resume. Just take note of that, okay? So it's Dr. Adifokun, TC, signing out on this day. Today is I think today is 11th of April, March 2023. So keep safe. Thank you.